Hello, everyone, and welcome to my talk. My name is Pierre, and today I'm going to be talking a little bit about the independent research I've performed as part of my doctorate at ETH Zurich. If you're not familiar with ETH Zurich, I can post some more information about it below. But originally, this presentation was meant to be part of my public PhD defense. However, given the current coronavirus situation, these were all canceled. But I still felt that I should make this presentation and share with you some of the research that I've done. Now, keep in mind that the intended audience for this presentation were undergraduates, graduates, and professors with science backgrounds. But of course, if you don't fit this background, I'd be happy to help you learn more about it. Feel free to ask any questions you'd like. So the title of this talk is Exploring the Importance of Multidimensional Quantum Tunneling Pathways in Atmospheric Chemistry. I'll get into what some of these things mean later, but first let's focus on atmospheric chemistry. And let me make sure I have my laser pointer working. Yes. Okay, so let's look at what I mean by atmospheric chemistry. Here's actually a picture I took of Mount Everest while I was traveling in Nepal. And Mount Everest is about 9 kilometers above sea level. What chemists consider the atmosphere, however, is everything from sea level up to 100 kilometers, right? And this is what we call the Kármán line at 100 kilometers. So everything up to here is in the domain of atmospheric chemistry, let's say. And in order to study the chemistry, we need to know what kind of environment it's in, right? So what are the temperatures? Well, near sea level, we have temperatures around 300 Kelvin, and at the Kármán line, it goes down to about 180 Kelvin. The pressure changes quite a lot by 7 orders of magnitude in pascals. And what kind of composition are we working with, right? So what kind of atoms are making up the molecules in the atmosphere? And we see that we have a lot of nitrogen, oxygen, carbon, hydrogen, and noble gases. Now, it turns out that the tools we use for atmospheric chemistry can also be applied to interstellar chemistry, right? So the chemistry that's going on in space. And well, this is not a picture I took, unfortunately, but maybe one day I'll be an astronaut. But let's look at what are the temperature conditions here. So starting from the Kármán line around 180 Kelvin, it drops down very quickly in temperature to roughly 10 Kelvin in the interstellar medium. And the pressure changes here are even more significant. So we have 12 orders of magnitude difference in pascals. And we see that actually the atomic composition is very similar. So we still have a lot of hydrogen atoms, oxygen, carbon, and noble gases. But in general, the chemistry I'm going to talk to you about today is going to occur at low temperatures, over a wide range of pressures, and for atoms with relatively small masses. So one last thing before we get into it, I wanted to mention one thing about thermodynamic ensembles and what do they mean. So typically when we work at sea level, chemists are working in a high pressure condition around 10 to the 5 pascals. And in these cases, we use what's called the canonical ensemble. What this means is we theoretically take a box of microstates or molecules and we define one temperature which gives rise to a Boltzmann probability distribution. So basically we have one temperature defining our system, and this temperature is going to define the probability that each molecule is in a given energy. And you can see this Boltzmann distribution given here by this green line. However, as I mentioned, as we go up in the atmosphere or even into space, we work at very low pressures. And in low pressures, we don't have molecules hitting your reactant or product all the time. And so you don't have this distribution of energies. What you get instead is a microcanonical ensemble. And the way to think about this is it's the same box of microstates, but instead of one temperature defining the system, it's one energy defining the system, right? So think you're a molecule traveling in space, there's nothing else around, you're going to travel for a very long time with your same energy before hitting another. Another term for this is the mean free path in space is very long, and so there are no collisions with which to change a molecule's energy. Okay, so just keep these thermodynamic ensembles in mind, and we'll come back to them. Now, I'm going to present the two major research questions for this presentation, and we will be answering these throughout the talk. So one, are nuclear quantum effects important in kinetics? I'll go into a little bit about what nuclear quantum effects are, and we just want to know, are these important in determining the rates of chemical reactions? And we're hypothesizing, yes, they are, because we are working at low temperatures and with atoms with small masses. The second question we want to answer in this talk, can these nuclear quantum effects be accounted for in rate constants? And the rate constants should be formulated in a canonical as well as a microcanonical ensemble so that we can use them to model atmospheric chemistry as well as interstellar chemistry. So what are nuclear quantum effects? So the first one that people may be familiar with is quantization, which gives rise to zero-point energy. So here we have a profile of a reaction coordinate where here's our reactant well going over to products. And the nuclear quantum effect of quantization gives rise to these energy levels. And so a molecule can only occupy one of these energy levels at a time. Now, in the classical limit, when chemists talk about the classical limit, we talk about high temperatures and large masses. And when you have this kind of high temperature and large mass, you'll see that the reactant, if we play this video, actually has a lot of energy and can pass over this reaction barrier through what's called a transition state and form products. So this is typically how we would think of a classical reaction, and theories like transition state theory make use of this exact idea, but they do include the nuclear quantum effects of quantization. Now, when we go to the quantum mechanical limit, you can think of it sort of as the opposite of the classical limit, where we work at low temperatures and small masses. You, of course, have the same effect of quantization, but a second nuclear effect that we now need to consider in the quantum limit is this idea of tunneling. So this multidimensional quantum tunneling that I spoke about in the title is a nuclear quantum effect that's actually very important at low temperatures and for atoms with small masses. And what you saw in the video is that the reaction can occur either by going through the transition state if it has enough energy, or it can actually tunnel through the reaction barrier, right? And so we want to incorporate this idea into our kinetics. One slide I have here for you is actually experimental results, and we're going to be looking at this H plus CH4 reaction, where you have an H atom abstracting one of the hydrogens from a methane molecule. And many people have performed experiments on this reaction, and you can see here in the plot, on the y-axis we have, on a log scale, the reaction rate constant. So the higher the rate constant, the faster the rate. And on the x-axis is 1000 over the temperature in Kelvin. So as we go this way, the temperature is decreasing. This is very low temperatures, as you can see here. And what we see is that as the temperature decreases, the rate, of course, decreases. However, if we use a classical limit theory, such as transition state theory, we would get a line that looks something like this. And this is curious, right? So what is this discrepancy? At very low temperatures in the quantum limit, the true or the experimentally observed rate is actually much higher. You can see 2 to 3 orders of magnitude higher than the transition state theory rate. And we can attribute this to the nuclear quantum effect of tunneling, right? Because both of these are going to already have quantization, but transition state theory won't have that nuclear quantum effect of tunneling incorporated. A different experimental way to show that tunneling is important is on this plot here, where on the y-axis we have the rate of this reaction of this being a hydrogen, and they also performed the experiment with this atom here being a deuterium. So the same, basically the same configuration, just making this mass bigger and seeing if that affects the reaction. And of course, we see that it does. So as the temperature decreases, the difference in these rates increases. And this is just more experimental evidence that quantum tunneling is important at low temperatures. So I think we can quickly just answer this question. Are nuclear quantum effects important in kinetics? I would say yes. There's much experimental evidence to show that at low temperatures and small masses, they are important. But now for the real big question, can they be accounted for in rate constants? So first, let's look at the canonical rate constants. So typically, what I talked to you about earlier about transition state theory, that is considered classical theory. And the rate constant is proportional to the exponential of this V double dagger, which is the potential energy of the classical transition state. And we saw that this does not always reproduce the experimental results very well. If we want to reproduce experiments very well and increase our accuracy, we need to use theories that rely on quantum mechanics. And in the fully quantum mechanical exact formulation for a rate constant, we would have to, instead of looking at the classical transition state theory potential energy, instead we're actually going to have to sum over the exponential dependence of all pathways going from reactants to products. And these pathways have an associated, what we call action S. This S variable stands for the action of those pathways. But typically, this is very, very expensive to do. It's technically impossible to sum over all the infinite possible pathways. So instead, what have people done? So typically what people do is use a transition state theory like rate, and to incorporate the added effect of one-dimensional tunneling, people use some approximations to the classical rate. So this includes things like WKB approximation, small curvature tunneling, semi-classical transition state theory, etc. So these are one-dimensional approximations to the rate constant, and they still all rely on this potential energy of the transition state. The approach that I'm going to talk to you about, and what I've been working on actually, is the opposite. So we actually start from the quantum expression for the rate constant, and we make an approximation out of that, right? So we move this way instead of moving this way. And this approximation is called the semi-classical approximation. And what we get is what's called instanton theory. And this is what I have been working on during my doctorate. So what is this semi-classical approximation? Well, here you can see, just very generally, I'm going to call this a reactant and it's a product in a chemical reaction. And it starts at some position and time, and it forms products at a later position and time. And the pathway going from reactants to products is what I was mentioning before, that has an associated action with it. And in the fully quantum mechanical limit, we need to incorporate all possible pathways, right? So we have to follow all of these and sum up all of the actions, or the exponentials of the actions for all of these pathways. And what the semi-classical approximation does essentially is actually only look at these few pathways here, in which the action barely changes if you move along it, right? So it's stationary in the action. Maybe a more easier to understand or pictorial view of this would be the following. This is actually a picture of a tree I took in Cambodia. And this reminds me of the semi-classical approximation. So if you think of the reactant of this tree being a little seedling in the ground, and the product being the full tree as it's grown up, you can see that the pathway from reactants to products can take many different paths, right? So as this tree grew, it took many different pathways, and it had to go through some of these ruins, some of this stone, right? So there was a potential energy barrier to this reaction. And what the semi-classical approximation is saying is ignore all of these little branches and roots and pathways that you see here, and only include the main dominant tunneling pathway, which would be the tree trunk on the inside of this tree. Right, so the semi-classical approximation, think of that as being, let's just look at the dominant pathway that tunnels through the potential energy barrier. And this is exactly what the instanton is, right? So another pictorial description of this I'd like to share with you is the following. So this is a potential energy surface. I've made it look like a hiking map. Maybe if you're hiking in Switzerland, you've seen a map like this. But let's say we start in this valley over here, and we want to hike to the center of this lake over here. And so typically, how would we do this? Well, in a classical sense, we find the pathway that requires the least energy, right? So this is called the minimum energy pathway if we want to go up here through this saddle point and down into the water. And if we do this, if we do follow this, this is called the minimum energy pathway. And this is a very useful tool. In the classical limit, it works very well. But another path you could consider taking is a minimum distance path. Let's say you don't have enough time to hike today. Well, we need to get there quickly, and so let's just go directly, forming a line between these 2 points. You can see, however, that in order to do this, you're going to require a lot of energy because you need to get over this mountain here in order to get there as fast as possible. So typically, what we see in nature is that actually neither of these pathways are taken, and instead, what we see is a minimum action pathway. So whichever pathway minimizes the action from the reactants to the product area is actually the one that nature will take, and that we would probably take in this case as well, right? We would take a shortcut instead of taking this longer route. And this instanton is the minimum action pathway. It's the dominant tunneling pathway that we saw from the previous slide. And what's really interesting about this is that we can formulate it such that it's actually energy dependent or temperature dependent. So you can see at different energies, we have different instantons. And as the energy or the temperature increases and we approach the classical limit, it actually converges to the classical transition state, right? So this is cool. We have instanton theory, which is a semi-classical theory that takes us from the classical to quantum limits, depending on what temperature we're at. And I've shown you pathways, but how do we computationally implement these, right? We can't just put a pathway in a computer. We need some way of numerically determining these things. And we use what's called the ring polymer isomorphism. So first, let's just look at normal transition state theory. What we do in this theory is we look at the reactant and the transition state, and we can formulate our rate constant expression like this. It's the ratio of the partition function of the transition state and reactants. And then, as we saw before, it's also proportional to the exponential of the potential energy of this transition state. Now, if we use the ring polymer isomorphism for instanton theory, we get actually a very similar looking rate, right? So the rate constant for ring polymer instantons looks like this. We have the same prefactor. We also have this ratio of partition functions, but instead of the transition state now, we have an instanton pathway, right? We don't have this transition state anymore. That's a classical idea. At lower temperatures, we have an instanton instead. And instead of the potential energy of the classical transition state, now we look at the action of this pathway. And because it's a pathway on this potential energy surface, it's actually a large set of independent geometries, whereas the classical transition state is just one geometry. So this instanton is discretized into a number of what we call ring polymer beads, and this is how we numerically implement our theory. Now, here's some experimental work in which we compare our theory. So again, we have the rate constant on the y-axis and 1000 over the temperature on the x-axis. So this is called an Arrhenius plot. And again, we plot classical transition state theory in yellow. We have experimental results in black circles and white circles. And we also compare exact quantum mechanical calculations to our blue instanton calculations. And we see that they line up very well. There's really a very small error maybe here. But in general, our instanton theory does very well at predicting canonical reaction rates, and we can use them to model other reactions as well. So I hope that I've convinced you that we can account for nuclear quantum effects in canonical rate constants, and we did this using instanton theory. Now let's look at the more interesting case of microcanonical rate constants. So why would we be interested in microcanonical rate constants? Here I have a video showing a reaction which is occurring in the atmosphere and which has also been experimentally tested. We have an OH radical, which is very important in the atmosphere for scavenging other molecules. And here it's attacking a methanol molecule and ripping one of the hydrogens off, forming water. And why would we need microcanonical rate constants to model this reaction? Well, it turns out that when the OH molecule approaches the methanol, it forms actually what we call a pre-reactive complex. So before the reaction actually takes place, the OH and the methanol form this complex, which is vibrationally stable. So it does actually save energy by being in this conformation. And what this does is it incorporates pressure dependence into a reaction. So let's first look at the low pressure case, right? So in the low pressure case, you have an OH molecule that's been traveling in the atmosphere or in space for a very long time. And it has a given energy because it has not collided with anything. And its energy doesn't change. And as it collides with this molecule, they also don't collide any other bath gases, and they just continue on with that energy, right? So this is what I'm depicting here. At low pressure, we don't have any collisions, and the reaction continues to occur at that given energy. And this is why we would need microcanonical rate constants. In the high pressure limit, however, as these molecules come together, collide, form a complex, in the high pressure limit, there's also molecules all around which would collide and give rise to more of a thermal distribution, right? A canonical ensemble. And so in this high pressure limit, the energy of the complex actually gets stabilized because some of this energy goes out to the bath gas. And in that case, we could use a canonical rate constant to model that. Now, how do we normally calculate microcanonical rates? And so here is a very famous theory called RRKM theory, which gives rise to this expression for the microcanonical rate. On the denominator, we have rho of the reactant. This is the density of states in the reactant at that given energy. And in the numerator, we have a sum of states in the transition state. Right, so this is again a classical limit view of the microcanonical rate, but it's saying that the rate is dependent on this ratio, where the sum of states in the transition state is how many states can be populated at this energy, minus the classical transition state energy. And the denominator is going to have how densely populated are these reactant states coming out of this well. And if we wanted to calculate the sum and density of states for this reaction, we can look at the complex of the OH plus methanol reaction that we already saw. And here I'm going to be plotting on the top here the sum of states, and on the bottom here the density of states, using two different algorithms. Right, so we can actually count these microstates using some algorithms that have been developed just for this. The very famous one is called the Bayer-Swinehart algorithm. Here I just abbreviated BS. And what we can do is count the number of states in the complex. So in this case, we're just looking at the reactant. And we can also calculate the density of states using this. WR is the Witten-Rabinovich approximation to the exact sum of states. So this, in many cases, could be a lot cheaper to calculate, although not as accurate. And you can see actually here, there is a little bit of discrepancy between those two algorithms. So let's zoom in on that. And what you see here is, again, the log scale of the sum and density of states, the number of states, as a function of energy. And you can see in the blue case, which is the Bayer-Swinehart exact counting algorithm, you have really this jagged, stepwise looking function, which is actually the true sum of states in this case. Sorry, this is the sum of states and this is the density of states. And what we see is that the green Witten-Rabinovich approximation does not perform well at the very, very low energies, but it's still very useful at intermediate and high energies. And we use both in our work to calculate these expressions. Now, what's also really interesting is that you can see for very low energies, you really can see this quantization of states. And as the energy increases, you see this beautiful progression from the quantum limit to the classical limit. So I already showed you the RKM rate constant, but we can actually incorporate instantons with RKM theory to give what I'm going to call the RKM instanton rate constant. And the way we do that is first we formulate P of E, which is a reaction probability for that ring polymer instanton. And again, that's going to be proportional to the action of that instanton. Using this reaction probability, we can create a cumulative reaction probability. So we sum over all of these reaction probabilities at that given energy and all energies below it given by a harmonic oscillator, right? So if we remember, the reactant state had quantized energy levels. If a reactant is coming in at a given energy, the cumulative reaction probability is going to include that reaction probability plus this one, plus this one, plus this one, right? So we need to include all energies belonging to those harmonic oscillator quantized states. Now that we have a cumulative reaction probability, we can actually put this in the numerator of the RKM rate constant, right? You'll notice this was very similar form, but here, the only difference is that we're looking at the total energy instead of the energy minus the V double dagger, minus the potential energy of the transition state, because in ring polymer instanton theory, we can tunnel through the barrier. So we don't have to limit ourselves to just those energies. We can really look at all energies here. And yeah, so now we have an expression for the microcanonical reaction probability, which includes tunneling and quantization, right? These two nuclear quantum effects that were so important. So let's see how it performs. Here is a reaction, it's called the Kriege intermediate, or it's a Kriege intermediate. And what we see in this reaction is a unimolecular hydrogen transfer, right? So initially the hydrogen starts here attached to this carbon, and the reaction is its transfer over to this oxygen. And this is a very hot topic molecule to be studying in atmospheric chemistry, and so we wanted to see how we can perform and if we can compare it to experiment. So here you see the microcanonical rate constant as a function of energy, increasing energy, where this line is giving the energy of the top of the potential energy barrier, right? So if we had a classical theory, we would not be able to get any of these points, and we would only be able to start at energies higher than this barrier. However, since now we're working with ring polymer instanton theory and including tunneling, we can, and we see that actually our instanton theory, given by the circle here, matches up exactly with experiment. to within a given error bar. So this is super exciting, right? We can, without even doing the experiment at all, we've been able to formulate a microcanonical rate constant, and we're able to predict the rates of reactions without ever having seen them. So this is really cool. Shown in stars here are different approximations to the tunneling pathway. So I hope that I've answered this question. Can these canonical and microcanonical rate constants be formulated such that they incorporate nuclear quantum effects? Here are some of the references in case you're curious, and I've also put the slides that they appear on. And lastly, I'd like to give a big thank you to ETH Zurich, the Department of Chemistry, and the research group, the funding sources, Swiss National Science Foundation and MeWell. Of course, thank you to friends and family along the way. And I'd also like to give a big thank you to some of the organizations I've been involved in, the Analytics Club and the ETH Student Project House, for a lot of the data science projects I've been involved in. And I've also helped co-found this organization called MeWell, the Mental Wellbeing Community. And essentially, this is a student-run nonprofit organization in Zurich, and we aim to increase awareness about mental well-being in academia, as well as offer a peer support community. And we also want to be like a hub of readily available information for people to access. We're always looking for people to join, so we'd be really happy if you are interested. So I'll post links about that below as well. Thank you very much. Has been great sharing this with you, and please let me know if you have any questions.